Student of 11th Science, welcome back to Division Physics classes. Today we start with our new chapter Work, Energy and Power. First we know about the concept of work. In our daily life, we often use the term work. For example, your mom preparing the food for yourself, then you can say your mom is doing some work. Similarly, whenever you read your book, then your parents can say my child is doing some work. But this is the concept of work in our daily life. The concept of work in physics totally different from the concept of work in our daily life. In case of physics, to know about the work, you have to know the external force acting on an object and whether there is a displacement takes place of the object or not. In case of physics, we can say work is said to be done by an external force whenever the application point of the external force is displaced along the direction of force. For example, see, an engine pulls a train. Whenever an engine pulls a train, the engine will provide some force on the train. That's why the engine will do some work on the train. Similarly, a man goes up a hill. Whenever a man goes up a hill against the gravity of earth, the man will do some work. Clear? So now, you have to know the measurement of work. To know about the measurement of work, you have to know the nature of applied force on the object. There are two types of force may act on an object. Number one, a constant magnitude force, and number two, a variable force. Today we know about the measurement of work whenever a constant force acting on an object. So now see the board. Work done by a constant force. Now the constant force acting on the object in two different ways. Number one, when force act along the direction of motion. What is the meaning of this line? The meaning is that the external force acting on the object and the displacement of the object are in the same direction. Just see the diagram. This is the direction of external force and this is also the direction of displacement of the object. Then the work done can be calculated as work done is equal force into distance moved along the direction of force. So therefore W equal Fs. So whenever force and displacement of an object are in same direction, then work done can be calculated by taking the simple product of force and displacement, that is W equal Fs. Secondly, when force and displacement are inclined to each other. See the diagram. Okay. On this object, we are applying the force in this direction, but the displacement occur in this direction. Means the force and displacement are acting on the object in two different directions. According to this figure, we consider theta be the angle between force and displacement. Then how can you determine the amount of work done? In this situation, whenever force and displacement are in different direction, to determine the work done, you have to take the component of force along the direction of displacement. From the vector analysis, we know that the component of force along the direction of displacement is F cos theta. Okay, after determining the component of force along the direction of displacement, you have to take the product of displacement and the component of force along the displacement, which gives us the amount of work done. So therefore work done is equal component of force along the direction of displacement and the magnitude of displacement. So therefore W equal F cos theta into S, or W equal Fs cos theta. From the dot product of vector, Fs cos theta can be written as F vector dot S vector. So therefore W equal F vector dot S vector. Okay, so means from this mathematical expression we can say work done is a scalar quantity. Why? Because the dot product of two vector always gives a scalar quantity. This is very important things you have to remember. Okay, so means from here a question may asked in your paper that name a physical quantity which is scalar but it is the dot product of two vector quantity. Your answer will be work done. Work done is a scalar quantity which is the dot product of force vector and displacement vector. After knowing the measurement of work done by constant force, you have to know about the nature of work done in different situations. Nature of work done means by the external force, work done is positive or work done is negative or work done is zero. You have to know. So first we know about positive work. When theta less than 90 degree, this type of angle is called acute angle. Then the work done is positive. Why? Theta less than 90 degree means the angle between force and displacement is less than 90 degree. And for any value of cos less than 90 degree, cos always gives the positive value. That's why the work done is positive. Example, when a body falls under gravity, then the displacement occurring vertically downward direction and the gravity of earth is also acting vertically downward direction. Means the angle between them is 0 degree and cos 0 1. So therefore work done by the gravity of earth for a falling object is always positive. Second example, when a spring is stretched, then the work done by the stretching force is positive. See the situation. You just take a spring and you give some external force to stretch the spring. So means your applied force and the displacement of the spring. Displacement of the spring means increase in length of the spring occurring same direction. Here also theta equal 0 degree means the work done by the stretching force on the spring here also positive. Next, negative work. When theta greater than 90 degree, this type of angle is called obtuse angle. Now, whenever the angle between force and displacement greater than 90 degree, for any value of theta, cos theta is always negative. That's why we can say work done is negative. For example, you just throw an object vertically upward. Then the displacement occur upward, but the gravity of earth acting downward. So means the angle between the gravity of earth and the displacement is 180 degree. And remember, cos 180 is minus 1. So therefore work done by the gravity whenever an object moving in the upward direction is negative. Similarly, suppose this is an object which is in motion over my hand. So between this object and my hand there will be a force of friction which is acting opposite direction to the direction of motion. So therefore angle between the displacement and the force of friction is 180 degree. So therefore cos 180 minus 1. So work done by the force of friction during the motion of an object is also negative. And lastly, you have to know about zero work. There are two different types of situation may arise for the zero works. Number one, whenever theta equal exactly 90 degree, because cos 90 0 means work done is also 0. For example, whenever any object revolve in a circular path, suppose here an object revolving in a circular path in anti-clockwise direction. During the motion along a circular path, the centripetal force and the displacement always makes an angle of 90 degree. So therefore work done by the centripetal force here is 0. Similarly, during the oscillation of simple pendulum, the tension acting on the thread of pendulum always makes an angle of 90 degree to the displacement of the bob. So therefore work done by the tensional force in case of simple pendulum is also 0. Another situation, you are applying the force but there will be no displacement, means S equal 0. So therefore from the formula W equal Fs cos theta, we can say work done is 0. For example, whenever we are pushing a wall, we are giving some force but the displacement of the wall is 0. Then also the work done is 0. And this kind of force is called workless force. Okay, so this is the three nature of the work which is totally depends on the angle between the force and displacement. Now we have to know the dimension of work. According to the definition, W equal Fs. So therefore dimension of W equal dimension of F into dimension of S. So dimension of F is mLt to the power minus 2, dimension of S is L. So therefore dimension of W equal M, L into L square T to the power minus 2. So therefore this is the dimensional formula of work done. Thank you student. I request to all of you, please see all my video. I think this will help you. Thank you again.